We learned a lot about Proposition 65 and the obligation we have as an industry to warn our consumers or our customers of any hazards that may be contained in our product. As the first speaker after lunch, I feel compelled to warn you that my comments may cause drowsiness and maybe even a loss of consciousness. Having said that, I'm now off the hook, and it's your responsibility. What I'd like to talk about today are some studies that we've conducted on ceramic labels that are placed on glass containers. That's the major portion of our particular focus as American Glass Research is glass bottles. Specifically, I want to talk about the stresses that are created when you put ceramic labels on glass containers, and there's a mismatch between the coefficients of expansion of the decoration and the bottle. Now, ceramic labels have been applied to containers originally on refillable bottles going way back 60, 70 years ago. The idea was that you could apply the label one time and it would survive through the life of the bottle. Now, at that time, filling lines were very local, very regional, serving a very limited geographic area. So it was fairly easy for retailers, for the fillers to collect these bottles, bring them back to the filling line where they would subject them to hot caustic solutions to remove any residual product that might still be in the bottle and to cleanse the bottle from dirt and contaminants and junk that may have accumulated on the bottle during its storage. Now, these bottles would remain viable until two things occurred. Either the scuffing on the glass surface became too severe and become objectionable. And we have one example here of this Pepsi bottle where the heel contact region is very severely scuffed, and this Coca-Cola bottle where the shoulder and heel contact points are fairly severely scuffed. So the filler would assess the degree of scuffing, and if it became too severe, visually objectionable, the bottle would be removed from the float. The other issue was the integrity of the label itself. Even though these ceramic labels were relatively impervious to the caustic solutions, they still reacted to a certain extent, and the caustic would eventually compromise the integrity. And you can see that here on this 7-Up bottle. The label itself has lost some of its distinctness. The color has started to be muted and faded. And especially up here in the neck, this little 7-Up logo is invisible now. You can't even detect it. The other issue becomes visible or evident here with this little logo on the Pepsi-Cola bottle in the back. The logo is starting to lose its integrity. And so because of the loss of either the ACL integrity or the scuffing of the bottle would be removed from the float. It would take many, many years to do that. More recently, ceramic labels have been applied to non-refillable bottles. Now, the interesting part of this is that you're not putting the label on for longevity. These bottles are going to be used one time only, and discarded. But the ceramic labels were applied to impart the appearance of a premium product. Very sharp colors, sharp graphics. The feel of the bottle is one of premium quality. Now, in very general terms, when decorations are applied onto glass bottles, they generally consist of, the raw materials generally consist of three components. A low melting temperature frit and colorant, which is then dispersed uniformly in some type of hydrocarbon carrier, so that the material, when it's applied to the surface of the room temperature bottle, would be consistent in thickness, and that the frit and the colorant are uniformly distributed to achieve the desired effect of that particular label. These decorated room temperature bottles are then slowly heated up to some elevated temperature. During the initial stages of the heat, the hydrocarbon carrier or this dispersing agent would be volatilized. The glass bottle is then continued to be heated up to a temperature somewhat in excess of 600 degrees centigrade. at which time that low melt temperature frit and colorant are now molten, fused to the glass surface. Now we have a slight dilemma. The annealing point of soda lime silica glass containers is about 550 degrees centigrade. And by going up to slightly above 600, we are now well above the annealing temperature. And so once the material has been fused, molten, and we begin to cool the container, we have to be very careful about the cooling rate. It has to be controlled by the thickness of the glass container itself. And so the rate of cooling has to be within certain boundaries, or we would end up destroying the annealing state of the container. And that could be a problem, and I'll explain that in a few minutes. Once we get below the strain point of the glass, which is around 510 centigrade, then we can start to more rapidly cool the glass container down to room temperature. Once we achieve about 100 degrees centigrade, maybe 125, then we would reapply what is called the cold end coating. This imparts some lubricity to the glass surface to allow the containers to more easily flow through the filling line in that process. Now, the reason that we were concerned about the stresses that are generated in the glass due to the differences in the coefficient of expansion is contained within this slide. It's fairly busy, but I want to go through it so that you have an understanding of why the stresses are so important. This is the fracture criterion for any glass object. It could be window glass, it could be goblets, tumblers, glassware, cookware, glass bottles, it doesn't matter. Glass will break when the tensile stresses that are created within the glass itself exceed the strength of the glass surface. When that happens, the glass will break. Now, the tensile stresses are going to be generated by the type of load that's applied to the container. It could be, for bottles, internal pressure, thermal shock, impact, vertical load. These are the four main types of loads that containers are expected to endure depending on their type of surface. The tensile stress that's going to be generated in the glass will depend on the magnitude of that load, the type of load that's being applied. It will depend on the design of the container, in other words, the structure of the bottle, and the thickness. These are all components that will determine the magnitude of that tensile stress. These are termed temporary stresses. They will only be present in the glass bottle as long as that load is applied. Once the load is removed, those stresses revert back to zero because glass is a linear elastic material and it returns to its original shape after being deformed. Now, the factors that affect glass strength is primarily the surface condition of the glass. Strength is not a material property of glass itself. Now, the surface condition is very important. If you have what is called a pristine glass surface, or one that is essentially free of any type of flaw, the glass surface strength could easily be in excess of 100,000 psi. Very, very strong material. If, on the other hand, the surface has been abused and contains a flaw that is relatively severe, glass surface strengths might be as low as a few thousand psi. It's a huge, big range. Now, the trick or the purpose of creating or performing design evaluations of glass containers is to make sure that the stresses that are generated by these applied loads are always lower than the expected surface strengths. There have been many, many studies conducted. We know what the expected minimum strength is for a refillable bottle, even after it's been abused for years and years and years. We also likewise know what the minimum expected strength of a non-refillable bottle is after one passage through a filling line. So this surface strength value is relatively known under normal, expected, typical conditions. It then is possible to design the bottle so that it has the proper features, proper thickness, so that under expected loads, those tensile stresses will be lower than the strength and the bottle will be viable. And that usually happens. It's the rare occasion that bottles break. Now, we have a slight problem here. These stresses that are generated in the glass result from the applied loads, which are temporary in nature, but stresses in glass are also additive. And so we have to always be aware of the fact that there could be permanent stresses inherent in the glass itself. And those inherent tensile stresses could be added with the stresses that are created by these applied loads. On this list are things like cord, which is a inhomogeneity in the glass itself that's coming out of the melting furnace. It could be annealing, which I mentioned earlier. If bottles are poorly annealed, there will be tensile stresses in the structure of the glass that exist for its lifetime until that container is broken. Also on this list is why you're here for the last day and the rest of today. These applied ceramic labels. All of these can be creating stresses that become inherent in the structure, are permanent, they exist until the bottle is broken. And if these are too high, they add directly with the stresses created by these applied loads. That increases the total magnitude of the tensile stress, oftentimes resulting in the values that are too high, higher than the expected surface strength, and the bottles will fail. So that's why we were primarily interested in conducting this study of trying to assess how much stress is actually created by these applied ceramic labels when the coefficient of thermal expansion is different than the glass itself. Now, the stresses in the glass created by these ceramic labels are easy to identify and they're easy to measure. For example, if we have this bottle over here on the left and we are interested in knowing how much stress is created by this red or white label, we can cut a ring section from that section of the bottle, depicted here, put that in a polarizing microscope, pass polarized light up through the thickness of the ring section, and we can assess the type of stress that's in the glass, and we can measure the magnitude of that stress with suitable compensators. This is a view of one of these ring sections in our polarizing microscope. This black line here is the ACL. By the way, we're looking down on the top of this surface here. The glass is to the lower left. The inside surface is out of our field of view down here to the lower left. This magenta colored region up here is simply the immersion fluid in which we have placed our ring section to view it. In this particular situation, the coefficient of expansion of the ACL is greater than the glass. By knowing how our microscope is set up, we know that this blue color is indicative of a compressive stress. As I mentioned before, through the use of suitable compensators on the polarizing microscope, we can measure the magnitude of that stress very easily. Here's a view, exactly the same setup, except now the coefficient of expansion of the ACL is less than that of the glass. The orange color here is indicative of a tension stress in the glass surface. And once again, we can identify that stress and we can measure the magnitude of that stress. That's very easily done. Now, when we come to the ceramic label, we have a problem, and that is due to the opacity of the ACL. We cannot directly determine what type of stress may be present in the decoration, nor can we measure the magnitude of that stress. It's totally impossible. So, what we have to do is, first of all, we make an assumption. If we see compressive stresses in the glass, we make the assumption that there are going to be tensile stresses in the ACL. On the other hand, if we see tension stresses in the glass, we make the assumption that there are compressive stresses in the ACL. That follows the basic law of physics and engineering, so we're not too concerned about making that assumption. It's essentially proven valid. Our problem is we don't know what that stress magnitude is. Down here at the bottom of this slide, we'll talk about this first. In the past, what we have done is we simply make the assumption that the stress in the ceramic label is going to be approximately equal to the stress that we can measure in the glass. Opposite in signs, of course, but approximately the same magnitude. Now, knowing that the ceramic label is thin, and it's a solid layer, we have to modify this assumption slightly by saying, yes, the magnitude may be similar, but most likely a little bit higher. How much higher? We have no idea. Now, ideally, you would like to choose your label material such that the coefficient of expansion of the ceramic label, once it's fired on the glass surface, has a coefficient of expansion that equals that of the glass. In those situations, there will be no stresses generated in either the label or the underlying glass substrate. In practical terms, this is very hard to achieve. I would even go as far as to say probably impossible. So if you know that you're going to have a mismatch, the way that that mismatch is supposed to go is that the coefficient of expansion of the ACL should be less than that of the glass. And that's what we've depicted here by that example where we see a tension stress in the glass, we know we have compression in the ACL. The idea here is that we don't want to put the ceramic label into tension. That's a tension stress that's exposed to the world, is subjected to becoming damaged through contact of labeled bottles during use. So we would like to have our ceramic label in compression, but now we become a little problematic here, and that is if this tension stress in the glass becomes excessively high, well then that can go back to our fracture equation or our criterion of if we have too much permanent tension stress in the glass, that could start to add with the tension stresses created by other types of loads. And so we became very concerned about this magnitude of the tension stress that's in the glass. We found a couple of references. There are many others, but here's two by Ray Andrews, formerly of the Drakenfeld, which became Faro, which, whatever. In his writings, as well as with other people, they talked about this situation of the coefficient of expansion of the ACL being less than the glass. And the comment was almost universally made that if that's the direction you go, if that's the kind of mismatch you have, then the magnitude of that mismatch doesn't matter. Yeah, I was concerned and confused as well, because what that does is it implies that the magnitude of this tension stress in the glass is totally unimportant. And it was very confusing to us, simply because of the fracture criterion. And so that became one of the purposes of us conducting this current study. First of all, we wanted to find out what is the relationship between the stresses that you can measure in the glass and the stresses that are then present in the ACL. Experimentally, you can't determine it, so we had to do it analytically. And then the second purpose was to evaluate this claim that we found in the published literature that if you have the desired mismatch, the magnitude of the mismatch doesn't matter. Now, we conducted our study by the use of finite element computer stress analysis. It's a very powerful tool, and this is a depiction of the model of the ACL itself, that's the dark gray, and the underlying glass surface is the lighter gray. And of course, it's much, much thicker than the thin ceramic label. We just depicted this here to try to give you an idea of the interface. Essentially, it was a model of a thin, solid film inherently attached to the underlying glass surface. Now, these are the parameters that we studied. We chose an ACL thickness of 1, 1.5, and 2 thousandths of an inch. These, through our experience, are about the right thicknesses for ACL materials applied to glass bottles. The glass thickness, we initially studied 0.09 inches, which is typical of the sidewall thickness of refillable bottles. If you remember, refillables were the ones that originally were decorated with these ceramic labels. Once we completed that analysis, we had some very interesting results, and we thought, let's go back, we'll repeat the analysis, but now we'll use a glass thickness of 0.05 inches, which is typical of the thickness of the sidewall of a non-refillable bottle, single trip bottle. Coefficient of thermal expansion of the glass, if you look in the literature, if you look on analytical methodology, soda lime silica glass has a linear coefficient of expansion of around 90. We chose 2 units below that and 2 units above that to try to encapsulate what most soda lime silica glass would show us. Now, for the coefficient of thermal expansion of the ACL, we wanted to bracket the coefficients of the glass. So we chose 2 units below and 2 units above, and had a range in between the two. And then, just for fun, we said, let's get crazy and say, what happens if the coefficient of expansion of the ACL is really high? So we chose 100 and 102. Now, one of the things that was inherent in our study is that we don't care how we got to these numbers. So we didn't worry about the chemical composition of the ceramic label. We were just choosing numbers to see what would happen if the coefficient of expansion were these types of values. Whether these types of values like 100 and 102 are feasible or practical, I don't know. It's fun whenever you're conducting computer analysis, you can do whatever you want. Now, here are some of our results. We have 3 plots. I need to take some time to explain what these plots are, on particularly this first one, and then you'll understand what's happening in the other 2. The y-axis is called the stress index. This is the output of the finite element program. It's a measure of the stresses that are developed either in the ACL or in the glass. The x-axis is the difference between the coefficient of expansion of the ACL and that of the glass. So if we take a look here at 0, the values to the right indicate that the coefficient of expansion of the ACL is larger than the glass. If we go to negative values, that indicates that the coefficient of expansion of the glass is larger than the ACL. Now, there's also a 0 axis here running through the middle of the plot. Stresses of higher than that number are indicative of tension. Negative values indicate compression. And that's the nature of these plots. Now, the first thing we wanted to look at was the effect of the ACL thickness. Remember, we chose 1, 1.5, and 2 thousandths of an inch. And what we're looking at here is the stress developed in the ACL itself. And you can see that the thinner ACL showed a slightly higher tension stress here, and a slightly lower, higher compressive stress down here. But overall, the effect of the ACL thickness, very, very minor. In fact, we said it's negligible. We're not worried about these very slight differences. What we saw also is that when the coefficient of expansion of the ACL was greater than the glass, we were creating tension stresses in the ACL. And when the coefficient of expansion of the ACL was less than the glass, we were generating compressive stresses in the ACL. What we expected. So, the effect of the ACL thickness, yes, there's a slight effect there, but overall, essentially negligible. We have the same plot, same kind of interpretation, except now we're looking at the effect of the glass substrate thickness. Now realize that our ACL is on the order of 1/1000th of an inch, and the glass is between 50 and 90. It's huge compared to our very, very thin ACL layer. And what we saw was, again, some slight difference depending on the substrate thickness, but overall totally meaningless, totally negligible. Now this first plot, where we looked at the variation of the ACL, the data values here are for a glass thickness of 0.09 inches. When we looked at the data plot for 0.05 inches, it was the same. Likewise here, we were looking at the glass thickness effect. These data are for a glass thickness of 0.09, for an ACL thickness of 1.5 thousandths of an inch. When we looked at 1 and 2, it was the same. So what we did is, this is a composite of all of our glass thicknesses, both glass thicknesses, all three ACL thicknesses averaged together. And we saw some very interesting results here. Once again, I want to remind you that negative values are compressive stresses, positive values are tensile stresses, positive X values are situations where the ACL coefficient of expansion is larger than the glass, and negative values along the x-axis indicate that the coefficient of expansion of the ACL is less than the glass. So let's take a look at this upper right-hand side first. Here we have coefficient of expansion of the ACL larger than the glass. We have tension being generated in the ACL, compression being generated in glass underlying. Now, remember one of the assumptions that we made way back when. We can measure this stress. The stress that's in the glass can easily be measured. And we don't know what the stress was in the ACL, so we had to make the assumption that it's going to be about the same magnitude, opposite in sign, and maybe a little bit higher. Well, as it turns out, it's quite a bit higher. In fact, the difference here between what we measure in the glass and what is observed in the ACL is on the order of 16 to 18 times higher. So what difference does that make? Here's what makes that difference. Let me explain what these pictures are, and then we'll discuss what is going on here. These were segments of the sidewall of a refillable bottle. We cut the bottle apart, and so that we could look at the interface between the glass and the ACL. We're looking through the inside surface of the bottle so that we can see that interface. And in many instances, when the coefficient of expansion of the ACL is larger than the glass, you can see micro cracks being generated in the ACL. And sometimes those micro cracks penetrate through into the underlying glass surface. And where we first encountered this was in fracture diagnosis of broken decorated bottles. These micro cracks are very hard, probably impossible to see if you're looking at the outside surface. But if you take a segment out of the glass and look at it through from the inside surface, and you get the light right, you can see them very easily. Now, these are two different examples, one here, one there, both showing the same effect. And what had always confused us was that when we measured the magnitude of the compression in the glass, we were only measuring maybe 300 psi. That's it. And remember, we were operating under the assumption that the tensile stress in the ACL would be approximately that same magnitude, maybe a little higher. It never made any sense. We were seeing micro cracks being generated in the ACL with a stress magnitude of a little bit higher than 300 psi. It made no sense at all. Now, once we have understood that the stresses in the ACL are significantly higher than the stress you can see in the glass, by maybe factors of 16 to 18, a compression stress of 200 to 300 psi in a glass means that you're probably seeing 3,000 to 5,000 psi of tension in the ACL. It's no wonder it's cracking. It has to. In fact, going back to some of Ray Andrews' publications, he talks about that, where if you get a large amount of tension stress in the ACL, you're going to see microcracks. And in fact, in some instances, this was the result of the failure of these decorated bottles. They were breaking at very low, normally applied load levels. And now it's suddenly starting to make some sense. Now let's go back to this slide, and let's look at this segment of the slide down here, this plot. This is where we are evaluating the claim that if the coefficient of expansion of the ACL is less than the glass, then the magnitude of that mismatch is unimportant. Now let's take a look at the data. When this coefficient of thermal expansion mismatch gets larger and larger and larger, we're seeing more and more and more compressive stress in the ACL. Once again, if you assume that the magnitude of the stress in the glass now would be about the same magnitude, we were worrying about the magnitude of that tension stress getting too high. Well, in fact, it doesn't. It's very, very nominal, as shown here. So, that contention for coefficient of expansion less than the glass, the magnitude of the mismatch doesn't matter. Now, what was interesting is that when we looked at these papers, not just Ray Andrews, but others, they never really had firm data, but rather it was based on anecdotal evidence that they were seeing from their practical experience. It's quite valuable. And they were seeing that if this stress, if the coefficient of expansion of the decoration was less than the glass, rarely ever produced any problems. On the other hand, if the coefficient of expansion of the ACL was greater than the glass, then that level of mismatch became very, very important. This is now some data that confirms the anecdotal practical evidence of very smart people over the years. So, the factors that are important is that mismatch and the coefficient of expansion. Now, I mentioned earlier that it's very difficult to get an exact match. And I don't think that's a problem with the suppliers of the ACL. I think they have a pretty good handle on what they're doing when they create the ceramic labels. I think the problem with the mismatch lies more in the hands of the glass manufacturer. Let me give you a small example. We had a problem where there were the viewing windows on microwave ovens or on regular ovens, they were fracturing. And they were decorated, So they sent them to us, and we measured the stresses that were inherent in the glass. And we found that the coefficient of expansion of the decoration was higher than the glass. When we reported that back to the glass supplier, glass manufacturer, he said, it can't be. Our glass hasn't changed. Well, a little more examination or investigation, the coefficient of expansion of the ACL was the one that was constant. And with a little bit of further exam or investigation, we found that the glass supplier was starting to use more cullet. And the cullet was throwing off his composition. And what used to be a coefficient of expansion of the glass that was higher than the ACL, through the use of cullet, it became lower than the ACL. He ended up with serious problems with cracking in the ACL. So the main issue here is the coefficient of thermal expansion. The glass thickness and the ACL thickness, yeah, there's a slight problem there, but minimal, not to worry about. These decorations, whether you're applying them onto refillable glass bottles or non-refillables, it's a viable way to decorate the glass and to label it, provided you pay attention to the stress that's created in the glass. And with that, I thank you very much for your attention, and you can cease being warned.
Questions for Gary?
Yes, sir.
Thank you. By the way, I knew Ray Andrews well, so it's good to see it's been substantiated. But in doing that, when you're actually doing the fit testing, do you have a range? For example, in the analogous flat glass business, we taught, and one of the say values that are plus or minus 220 psi versus the compression or tension. Do you have a range?
We've never developed a range. I have to admit that we haven't done enough studies.
Mm-hmm.
But I think in ASTM, there's something about plate glass and the fit.
Right.
And they only want a couple hundred psi of
C1048, ASTM C1048, yes,
Yeah.
that's what I'm referring to.
Yeah, I can't substantiate or refute that.
Okay.
I just don't have enough data.
Okay, thank you.
No.
Did you do any studies on decorated bottles versus non-decorated bottles? And what the tensile strength differences in a decorated bottle versus a non-decorated bottle?
Yeah. It's a very sensitive subject. And I will be more than willing to verbally discuss that. But I can always say, well, I can say that. Yes. Let me go back to an anecdotal event. It happened actually here in Western Pennsylvania. There was a glass company who was supplying bottles to a brewery, local brewery. These were non-refillable bottles, and everything was fine, no problem. Until the glass company, in conjunction with the brewery, decided they're going to take the half ounce of glass out to lightweight it. And of course, it goes back to that fracture criterion. You make the glass thinner, tensile stresses went up a little bit due to the pressure by the beer. All of a sudden, all heck was breaking loose. Breaking bottles in the pasteurizer all over the place. And what we found was that when ceramic decorations are applied to a glass surface, because it's fused to that glass surface, any kind of, I'll call them flaws, they're not really defects, in the ACL will affect the glass strength. And what we found were that voids, due to the volatilization of the hydrocarbon carrier, sometimes unfused particles, actually lowered the strength of the glass. And to be safe, what we adopted was that when we do a design evaluation, of a non-refillable bottle that's going to be decorated, we treat the glass surface as if it was a refillable surface. Because we know that the glass strength will diminish because of these decorations that are applied. I hope not a secret anymore, but I can't give you the exact numbers. Yeah, I could, but I won't.
Yeah, so you're saying it's a pristine glass bottle that hasn't gone through, might have some of these flaws just from handling, is going to be stronger than a decorated bottle, but over time, that if you continue to use that same bottle, as the flaws increase.
Yeah, that's the interesting thing with refillable glass. I don't have a chart here, so I'm going to draw my hand. A refillable glass bottle strength starts out relatively high. The first few trips through the filling line, the strength drops off fairly precipitously. But then, over time, that strength plateaus out to an asymptotic value. And the general picture is, as you put a refillable bottle through the filling line the first time, it picks up some damage. That diminishes the strength. As it is continually reused, it gets more and more damaged. In other words, you see more and more of the scuff bands. But the severity of the scuffing is about the same. So the strength plateaus out, even though the appearance gets worse and worse and worse, the strength isn't affected. So when you're doing design work, you know what that asymptotic value is. You design to meet that. With refillable or non-refillable bottles, yes, there's an expected strength of that glass at the end of a filling line, much higher than a refillable, obviously. However, when that's decorated, it reduces the strength to an unusually low number that you weren't anticipating. And that's what happened with this glass company. They took a half ounce of glass out of it, kicked them over the edge of the table. They put the half ounce back in and everything was fine again.